Hello, my young ones. It's Miss Lloyd. We are looking at linear equations in one variable today. I'm sorry, my voice is a little bit on the wrong side. Um, it's just been a really long week and a lot of talking that I'm not used to. So please bear with me. So the first thing we're going to look at is identity versus contradiction. So sometimes whenever you're solving a linear equation, your variables end up canceling out, and you could end up with two numbers that are equal to each other, two numbers that aren't. So if you end up with two things that are equal to each other, this is an identity. And so it's just saying that you can plug in anything for x, any real number for x, and you're going to end up with the same thing on the other side. Everything's going to be true no matter what you plug in. So say we have something like 3x is equal to 5x minus 2x. That would simplify to 3x is equal to 3x. You could subtract 3x to both sides and get 0 equal to 0, but even just looking at it in this form, we can see that no matter what we plug into x, one side is always going to be equal to the other no matter what. So this is an identity. We also have the instance where if we plug something in, no matter what we plug in, it's not going to be true. It's not going to work out. So in this case, it's called a contradiction. So say we have something like 4x plus 7 is equal to 4x minus 3. So here, if I end up subtracting 4x to both sides because I want my x's together, my x's end up canceling out and I have 7 is equal to negative 3. So this is telling me no matter what I plug in, I'm never going to get 7 equal to negative 3. No matter what I plug into x, the sides aren't going to be equal. So this is a contradiction. And so this would have no solution. There's nothing you can plug in that's going to make the situation true, the equation true. So when we're solving linear equations, I always like to see it as I like to see it as breaking your friend out of jail. So we're trying to get our variable alone. We're taking everything away from that variable, getting it off to the other side. Kind of like if you were breaking your friend out of jail, you're gonna like get rid of all the guards and then get into your friend to get them out, I guess. But basically, we're undoing the order of operations. So here, one of the first things I need to do, I want to get rid of the parentheses. And in order to do that, I can either divide by the 4 and the 5, or I can just distribute it in. So I'm going to distribute in so that I get rid of those parentheses. I've got 4x plus 8 minus 12 and 5x minus 30. Next, I want to get my variables together and simplify some like terms. So I have these two like terms, and I'm going to move the smaller variable to the other because I don't like working with negatives so much. I'm a positive person, so I like to work with positive numbers. So we end up with negative 4 and just x. 5 minus 4 gives us 1. And I want to get my x alone, so I have a minus 30 with it. I'm going to add that 30 to both sides. Negative 4 plus the 30 is going to give us 26. And so my x is equal to 26. And that's it. Ta-da! The next bit, my students kind of hate fractions. I always hated fractions when I was their age. I don't hate them anymore, but they're not my favorite thing to work with. So I like to use fraction as my F word. If someone cuts me off in traffic, I'm like, what the fraction, bruh? Because if I'm riding with my granny and I say the actual F word, then she smacks me. So if I say fraction, it confuses her and she doesn't realize that I'm cursing. She just hears the math and is like, what, why? So anyway, I always have this little chant that I have my students do. It's what do we hate? And then they yell fractions because they hate fractions. So they put a lot of passion into it. We hate fractions. So I say, well, what are we going to do about it? And then they just kind of look at me. And so remembering that a fraction is basically a little division, in order to kill it or murder it or get rid of it, we're going to use multiplication. We're going to use the opposite. So one thing we want to find first is the LCD. It's the least common denominator. It means we're trying to figure out what number can I multiply all of these by in order to get rid of each of those fractions. What I like to look at first when it comes to the denominator, or the LCD, is the highest denominator, so the one that's the biggest. In this case, the 9. So if I multiplied every single term by 9, would I get rid of every single fraction? So a 9 is going to cancel out a 9 if it's multiplying on top. A 9 will also cancel out a 3. 9 divided by 3 gives you a solid 3. I'm also going to multiply, oops, had 3 on the brain, my x and my last one here. So if I'm multiplying every single term, then I'm not really changing the equation. I'm just maneuvering it. So you could have tried to get every single fraction to look the same, and then you have a bunch of fractions. I just like to get rid of the fractions to begin with. So our LCD here was 9, and that's what's going to get rid of every single fraction. Sometimes it's not as easy as just looking at the largest one. You have to figure out what they can both become. So we're multiplying every single term. Next, we'll simplify each of the terms, and then we'll solve like a normal equation because we will have gotten rid of the fractions. So the 9 cancels out with the 9, leaving me just a 4x. I have 9 divided by 3 will leave me with just a 3, so minus 3. I have nothing to cancel out, which is the x, so that's going to stay 9x. And then I've got a 9 divided by a 3 here, so 5 times the 3 will give me plus 15. And now I just solve like a regular equation because I don't have any fractions to freak me out anymore. And my last step here isn't the most satisfying because as I divide both sides by 5, 18 and 5 don't divide evenly, so I'm just going to leave my answer as negative 18/5. And then I'm finished. Ta-da! All right, this next one I'm going to say for my bebés, it's just another example of what we just did, just a little bit more done out, and I would rather do that with them because I like them more than strangers I've never met before. No offense. If you are someone who is not one of my bebés and you are watching this, just, preferences. All right, so when we are solving some of these and we have variables in the denominator, we do have to be careful of extraneous solutions. So this is a solution that does not satisfy the original equation. So if we were to plug it back in, the signs aren't going, like one side, the left side isn't going to be equal to the right side. It just doesn't work out. We also have to be careful of if we end up with a 0 in the denominator when we plug stuff in. So most of the time when I start to check my work by plugging stuff back in, I start with the denominator and I plug things into the denominator to see if it would make it 0. If it doesn't, then I continue to solve out the whole thing to make sure that I didn't make a mistake or that my solution isn't extraneous. So here for the first one, I'm still going to do the same, trying to find the LCD. It seems a little bit more complicated now because we have some variables. It's not just a number that we're trying to get rid of. When I do this, I like to put this denominator, because I have a binomial, I like to put it as a factor in parentheses. So then I know this is like one entire thing that I'm trying to get rid of, not just multiplying by x, multiplying by a 4. I want to multiply by x minus 4 because it's the entire factor that I'm trying to get rid of. So every single term, I'm going to multiply by this x minus 4 so then it cancels out. And I'm also going to multiply it by that 5 because, again, it's every single term, not just the ones that have the fraction. So this first bit, whenever I go through to simplify, do my multiplication, I have the x minus 4s that will cancel out on the left, leaving me with just 3x. There's nothing to cancel out with the 5, so the 5 is going to distribute in to these parentheses, so I've got 5x minus 20. And then my x minus 4's cancel out for the last term, leaving me with just a positive 12. Now I can do my simplifying and solving because I don't have any fractions to freak me out. And so now I've got my 4. And again, I want to triple check that this isn't an extraneous solution. Just because you've solved and it's a nice pretty number or not a nice pretty number doesn't mean that it is the actual solution. So if I were to plug this number back into the denominator, so my denominator here is x minus 4. So plugging in 4 minus 4 would give me 0. So I can't actually use this number. I can't use the 4 because it makes the denominator equal to 0. So because that's the one thing that I found and that one thing doesn't work, we have no solution here. And unfortunately, it's not the most satisfying problem, but it is the correct way to finish this problem. So this one is a little bit similar. They want us to solve. We have fractions involved. Again, I have binomials in the denominator, so I'm going to see them as factors. And I see that y minus 1 and y plus 1 are different. So because they are different, I have to multiply by a y minus 1 in order to get rid of that first y minus 1. But that y minus 1 isn't going to get rid of the y plus 1. Only a y plus 1 will get rid of that. So in this case, I have to multiply by both in order to get rid of both. Sometimes, we have to do a little bit more to get rid of the things we don't want. And you can take that as a life lesson if you want. So I'm going to multiply every single term here, including my 0. So then going through each one, my y minus 1s cancel out. I'm left with my 5 and my y plus 1. My y plus 1s cancel out with the second term, so I'm left with that minus 4, y minus 1. And anytime I multiply anything with 0, even y's, I still end up with 0, so that doesn't really matter. Now I can solve as normal using my distribution and solving for my y, getting it by itself. So here I've got my y is equal to negative 9. If I were to plug negative 9 back into the original problem, then I wouldn't end up with any zeros in the denominator, so that means I can continue with it. So if I go off to the side, I'm going to check it. That means I'm just plugging in negative 9 everywhere I have a y. So it'd end up with negative 10 on the bottom, negative 8 there. So it'd have negative half, and then the two negatives would give me a positive here, half. Negative half and positive half would give me 0. So this one works out. This is a perfectly fine solution. So this is a little bit more of a satisfying problem because we actually say this is my solution to my problem. The next one I'm going to say for my babies. And the last thing we're going to look at is intercepts. So intercepts is where we're crossing the axes. X-intercept, we're crossing the x-axis. Y-intercept, we're crossing the y. So on the x-axis, y is always equal to 0. So if I have a little coordinate plane here, any point that I put along the x-axis is always something comma 0. So because I know this is something comma 0, I can plug 0 in for y and solve for my x, and I would find something that's along this x-axis. And similarly for the y-intercept, my x is always 0. So all along this y-axis are points that are 0 comma something. So because I know my x is 0 on the y-axis, I can plug in 0 for x to find any points that might be on that line. And again, sometimes we don't have points on that line. Sometimes we end up with like a parabola that looks like this. Sometimes we end up something that looks like this and it goes nowhere near it. And that's okay. So here for the first one, I'm not going to do the second one. I'm going to say that for my babies. We've got to find the x and the y-intercept. So I'm going to start with the x first. So that means I'm plugging in 0 for y. So instead of my y, I'm going to put 0 is equal to negative 3x minus 2. So I'm plugging it into the y that they gave me here. And now I'm just going to solve for my x, get the x by itself. And then lastly, I'm going to put it in point form. So my x was 2, negative 3, and that was when I plugged in 0 for y. So we know exactly where we're crossing the x-axis. We're going to do the same thing for the y-intercept. We're just plugging in 0 for the x that they gave us over here and trying to solve for y. So y, we don't know what it is yet. Negative 3, instead of that x, we're plugging in 0. And then we're just going to solve for y as normal, which was pretty quick. So when I plugged in 0 for x, we ended up with negative 2, and that is my y-intercept. And so that is all that I have for you guys today. If this was helpful for you, please like and subscribe. If you think that someone else would benefit from this video, please feel free to share it. Spread the love.